Okay, so what we have here is, what are these things? Speakers. So I have this guy hooked up to the same sine wave generator that we had earlier, and I have this guy hooked up to a different sine wave generator. And so in the class, one of the things that we talked about is we talked about beats, okay? And we talked about how to calculate beats, and I gave you like different problems. I said, if you produce one sound at 440 hertz and another sound at 444 hertz, what's the difference? What's the beats? 4, right? What if I produce one at 220 and the other one at 221? 1. Okay, now, if you've ever tuned an instrument, you've heard beats. But the funny thing about that is when I was in high school, I played the tuba. And I had no idea how to tune an instrument. I just had to have my friends do it for me because I couldn't understand what I was supposed to be listening for. So today, we're going to play some beats so that you can hear them. So before we do that, what is the frequency that this speaker's set on? 1. So that means it's going to produce 1 wave per second. In this case, sound is what type of wave? Longitudinal. That means it's compressions and rarefactions. So if you watch the speaker here, if I turn up the amplitude, you can see it's making a longitudinal wave. Y'all see that? It's compressing and rarefracting. Okay? How many is it making per second? Just 1. Okay? Now, can you hear this?
Yes.
Now you hear electrical hum. But can you hear this frequency?
No.
Yes.
No. And I can easily prove that because what you're hearing is, that's just this electrical hum here. It's the polarization of the electromagnet back and forth. Which would make perfect sense to you. So here's about 5 hertz, about 5 beats per second. So do y'all see that? Mm-hmm. Alright, so let's go up to something that you can hear. You hear that low, deep tone? Mm-hmm. That is the frequency of about 40 hertz. Alright? You can still hear that electrical hum, but this is the sound of 40 hertz. So if it's less than 40 hertz, it's going to sound lower than this. Okay? And so as I increase the frequency here to 60, so it's about 100 hertz. It's making a wave 100 times per second. And so this is 200. So if I change the frequency, it changes the pitch, right? So if the frequency goes up, what happens to the pitch? It goes up. So let's go to a pitch of my own choosing. So what number is this? What's the frequency?
220.
220. So this is the sound of 220 hertz. Everybody okay with that? So now I'm going to change this speaker to the same frequency, about 220 hertz. And I'm going to turn it all the way up. Did y'all notice any difference? Turn it down, turn it up.
Got louder.
Turn it up. Got a little louder. But it's the same pitch, or same frequency, so nothing's wrong. Okay, so now let's do some beats. So I'm going to change this guy by 1. Shh. Now listen, right now there's nothing funny. Okay, all I'm going to do is I'm going to change this by 1. Now here's 2. Here's 3. 4. 5. Y'all hear that? That wah 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 sound? And they're back on the same frequency. And so the beats are caused by the destructive interference of the waves. So right now they're the same frequency, so they're adding together and they're just louder. But when we have this destructive interference, then we have the waves kind of canceling out, and it makes this beat noise. Okay, so if one's at 220 and the other's at 222, what should be the frequency of the beats? 2. So you should hear 2 of these wah-wahs per second. Now, when we get to a frequency that's significantly off of this, the beats get so much that you can't even hardly count them. So this is just 230. So what's the frequency of the beats? 10. That sounds lovely, doesn't it? Alright, so any questions about beats?